Usually when we talk about a medical diagnosis,
Yeah.
there is this underlying expectation of precision. Like it feels almost like engineering.
Right, it's very binary.
Exactly. If a patient comes in with a broken arm, the doctor takes an X-ray, pulls up that high contrast image,
Mhm.
points to the jagged white line, and simply says, well, there it is. It's incredibly clean.
And we crave that binary, honestly. We love a world where problems can be, made completely visible and categorized neatly into a specific folder.
Treated with a standard protocol.
Right, a very standardized protocol.
But then you step into the world of neurodevelopment, learning trauma, and specifically the middle school mathematics classroom. And suddenly that pristine X-ray machine is just completely shattered.
Oh, absolutely shattered.
You're looking at a diagnostic landscape of struggling learners that is, honestly, it's murky. You can't just point to a failed math test and say, there's the
No,
broke.
you really can't. It is the absolute definition of diagnostic muddy waters. I mean, a student staring blankly at a worksheet isn't a singular symptom with a singular cause. That blank stare, it could be cognitive overload, it could be a profound executive function freeze, or, the crushing weight of ambient societal stereotypes, or maybe it's simply a lack of foundational arithmetic skills.
And often it's all of those overlapping simultaneously.
Exactly, all at once.
Well, welcome to the deep dive. Today we are speaking directly to you. If you are an educator, an instructional coach, an interventionist, or an administrator who is looking to utterly transform your classroom environment, you are in the right place.
You absolutely are.
We are diving into a massive, heavily researched stack of educational psychology, cognitive science, and modern pedagogical frameworks. Our mission for the next hour: to uncover the absolute most effective brain-based instructional practices for teaching middle school math to struggling learners.
Okay, let's unpack this because the stakes here are astronomically high.
They really are, because middle school is the crucible. It is this incredibly pivotal developmental transition where the nature of mathematics fundamentally shifts.
It goes from concrete to abstract, right?
Yeah.
Exactly. In elementary school, math is largely grounded in concrete arithmetic, adding physical blocks, sharing pizzas, counting money. But in middle school, we cross the bridge into the abstract symbolic logic of algebra.
Proportional reasoning, geometric proofs, all of that.
Right. And for students who arrive at this stage with foundational gaps, what researchers gently term unfinished learning, this transition doesn't just cause a bit of mild confusion.
It's much worse than that.
It triggers a massive systemic decline in their engagement with schooling as a whole.
And the data on this is staggering and frankly a little heartbreaking. Looking at the 2024 American Youth Panel, nearly 49% of middle and high school students report losing interest in math half the time or more.
Half the time.
Think about that. Half your room, half the time. 75% report periods of total, complete disengagement in any given class period.
Wow.
And if we look at the 2022 National Assessment of Educational Progress, the NAPEP, we saw an 8-point drop in 8th grade math scores. That isn't a blip.
No, it's a trend.
It is the largest single decline in the entire history of the assessment.
And when you look at those numbers, you start to see exactly why the traditional instructional model is fundamentally failing. I mean, the standard I do, we do, you do approach.
Where a teacher stands at the front and models a procedure.
Yes, and then asks students to copy that exact procedure 30 times on a worksheet. That actively punishes the cognitive mechanisms of a struggling learner.
Right.
In those traditional environments, up to 80% of students aren't actually learning. They are engaging in what researcher Peter Liljedahl calls studenting behavior.
Studenting. I love that term because every teacher recognizes it instantly. It's the mimicking, the stalling, the faking of understanding.
Oh, completely.
It's the kid who writes down the final answer from their neighbor without showing any work, or the kid who asks to go to the bathroom the second the independent practice begins.
Exactly. They're playing the game of school without doing the cognitive work.
So our goal today is to help you, the listener, transition from being an evaluator of right and wrong answers, just grading those mimic responses, to becoming a responsive architect of cognitive struggle.
I love that framing. A responsive architect doesn't just deliver information. They design an environment where thinking is unavoidable, where errors are diagnostic tools rather than moral failures.
And where the struggle itself is engineered to build literal brain capacity.
Right. But to build that architecture, we first have to look under the hood. We have to understand the biological and psychological roadblocks happening inside a struggling student's mind. Like, why do they freeze up before the problem even begins?
Well, because if you're standing in front of a class and a kid refuses to pick up their pencil, the instinct is to assume defiance. They just don't want to do the work.
Which is such a common trap.
But our sources point heavily toward cognitive load theory. It's not defiance. Their brains are experiencing a literal traffic jam. So let's break down this working memory bottleneck.
Yeah, cognitive load theory is arguably the most important framework for an educator to understand. It posits that human working memory, the active mental workspace where we hold, process, and manipulate new information, is incredibly, almost shockingly limited.
Like, how limited are we talking?
Cognitive scientists estimate that the average working memory can only hold about 4 to 7 chunks of novel information at any given time.
Wait, 4 to 7 total.
Total, and that's in an adult. When we ask a middle schooler to solve a multi-step algebraic equation, we are taxing that working memory to its absolute breaking point.
I always like to think of working memory like a computer's RAM. Your long-term memory is the hard drive. It can store virtually infinite amounts of information, like your childhood memories or how to ride a bike.
Right, the hard drive is massive.
But your RAM, your active processing space, is very finite. So let's say a student lacks procedural fluency. They haven't automated their basic multiplication tables.
This happens all the time.
Right, so if they are staring at an algebra problem,
Right.
and they have to actively open a mental browser tab and use cognitive energy just to figure out what 7 times 8 is, their RAM is getting eaten up.
That analogy perfectly illustrates the difference between what cognitive scientists call intrinsic load and extraneous load.
Okay, break those down.
So the intrinsic load is the inherent, unavoidable difficulty of the math concept itself, like the algebraic logic. If a student is burning all their available RAM on foundational arithmetic, their intrinsic load maxes out.
And the system crashes.
Exactly. They literally have zero cognitive resources left to process the new high-level algebraic software you are trying to install.
Wow.
But the traffic jam gets significantly worse when we introduce deficits in executive functioning.
Executive function being the brain's overarching management system, like the CEO of the brain.
Precisely. Executive functions live in the prefrontal cortex. They control working memory, but they also control task initiation, planning, sustained attention, and emotional regulation.
So for students with ADHD or dyscalculia or general executive dysfunction,
Simply starting a task requires an immense coordinated symphony of these cognitive skills. When these students are faced with a non-preferred, highly complex task like a page of math word problems, their brain perceives it as an overwhelming, insurmountable threat.
and this is where the biological response is fascinating. The nervous system actually shifts into a protective, sympathetic state. It's a literal fight, flight, or freeze response.
Right.
So when you see that student spending 10 full minutes just rummaging through their backpack looking for a specific mechanical pencil, or when they take one glance at the paper and immediately announce, "This is too hard, I'm not doing it," before reading a single word,
That isn't laziness.
right? That is a literal mental freeze. Their brain has shut down the prefrontal cortex to protect them from the cognitive threat.
And we often compound this threat with the way we talk about math anxiety. There is this pervasive misconception in education that math anxiety is just a feeling, a nervousness that students need to just push through or maybe take a deep breath to cure.
Let me actually push back on this because I think a lot of people listening might have that exact thought. We know anxiety is a psychological state.
Mm.
How does a purely emotional state actually change the physical mathematics happening in the brain?
It's a great question.
Like, does being nervous really stop you from being able to divide fractions?
It absolutely does, and cognitive scientists have mapped exactly how. Math anxiety is a profound cognitive disruptor. When a student feels that anxiety, it introduces intrusive thoughts and worries into the brain.
Like what kind of thoughts?
Thoughts like, I'm going to fail, or everyone is finishing faster than me, or the teacher thinks I'm stupid. Those intrusive thoughts don't just float in the background. They actively compete directly for the central executive resources in the working memory.
Oh, wow. So the anxiety is like an open browser tab playing a loud, unskippable video advertisement in the background. It's actively using up the RAM.
That's exactly the mechanism. The anxiety effectively shrinks the student's available working memory capacity. They literally have less brain power available to execute the mental carry operation in a complex subtraction problem because the anxiety is taking up physical space on their mental sketchpad.
The processing power is being diverted to managing the emotional threat.
Exactly.
Which brings us to a massive, incredibly heavy psychological layer that sits on top of all this cognitive biology. And that's the identity crisis and the legacy of failure.
Yeah, this is huge.
Because middle school isn't just about math. It's an intense, turbulent period of identity formation. And unfortunately, it's the exact time when the math person myth is aggressively amplified.
Right. The math person myth is the culturally ingrained belief that mathematical ability is innate. You're either born with a math gene and you see the numbers like Neo in The Matrix, or you aren't, and you are destined to struggle.
It's such a damaging idea.
It really is. In a traditional classroom, because of this myth, struggling with a problem isn't seen as a normal part of the learning process. It is viewed as a public, humiliating admission of a permanent intellectual deficit.
And the sources point out how this intersects in deeply problematic ways with cultural and gender expectations. Take adolescent boys, for example.
Okay.
In middle school, boys are often navigating hegemonic masculinity, this intense cultural pressure to appear stoic, tough, and naturally competent. For a 13-year-old boy, admitting that he doesn't understand how to find the common denominator of a fraction feels like a social vulnerability he absolutely cannot afford.
Right. It's a threat to his status.
So instead of asking for help, he acts out. He becomes the class clown, he flips the desk. Because in that social ecosystem, it is better to be seen as bad or rebellious than it is to be seen as dumb.
And the ambient cultural pressure is even more pronounced for marginalized students. Black, Latina, and Latino students often face profound racialized stereotype threats.
Stereotype threat. That's the psychological phenomenon where individuals feel they are at risk of confirming negative stereotypes about their social group, right?
Yes, exactly.
So walk us through what that actually looks like in the classroom. How does that impact the cognitive load we were just talking about?
Okay, imagine a Latina student sitting down to take a high-stakes math assessment. She is not just trying to remember the formula for the volume of a cylinder. She is acutely, subconsciously aware of the ambient societal narrative that suggests people who look like her are not supposed to excel in STEM fields.
Wow.
Navigating that pressure, trying to suppress the fear that her failure will confirm, the stereotype acts exactly like the intrusive thoughts of math anxiety. It siphons off her working memory.
So she's doing double the cognitive labor of a student who doesn't face that stereotype threat.
Exactly. She is fighting the math problem, and she is fighting a societal narrative simultaneously.
And this creates what the research calls the confirmation bias of failure. When a student has spent years internalizing this identity of being bad at math, it creates an impenetrable cognitive filter.
It really does.
If they take a test and fail, it seamlessly confirms their fixed mindset. It proves the narrative true. I failed because I am dumb.
Right.
But the true tragedy of this confirmation bias is what happens when they succeed.
Right.
If that same student gets an A on a quiz, they do not update their identity. They don't say, wow, I guess I'm getting better at math.
No, they attribute the success entirely to external, uncontrollable factors. They say, well, the teacher made the test really easy this time, or I just got lucky, or she graded it on a curve.
So the failure is internalized as a character flaw, but the success is externalized as a fluke.
Exactly. It is a completely self-sustaining cycle of disengagement.
Okay, so if we take a step back and look at this diagnostic landscape, working memory is severely bottlenecked. Executive functions are freezing up. Intrusive anxiety is draining the RAM. And the student's entire identity is barricaded behind a confirmation bias of failure.
It's a bleak picture.
It is. So if that is the reality, then standing at the front of the room and simply lecturing the steps of long division louder and slower isn't just ineffective, it's actively worsening the trauma.
It's instructional malpractice. It overloads the working memory with meaningless steps, it ignores the anxiety, and it reinforces the feeling of innate failure when the student inevitably forgets the steps the next day.
Right.
This is why we have to orchestrate a massive paradigm shift. We have to pivot entirely away from procedural mimicry and move toward thinking-based conceptual instruction.
Let's really dig into this paradigm shift. Because when you are teaching 8th grade and you realize a struggling student has these massive gaps in their knowledge, like they literally don't understand place value, but your curriculum says you have to teach linear equations today, the instinct is to panic.
Oh, completely.
A lot of educators use the analogy of a Jenga tower. You can't build on top if the bottom blocks are missing. So the traditional response is to stop, go backward, and try to drill those missing procedures. We put them in intensive remediation.
And decades of research show that traditional remediation, repeating failed instruction at a slower pace in a separate, isolated setting, almost never closes the achievement gap.
It doesn't work.
In fact, it often widens it because the student is perpetually kept out of grade-level thinking. I prefer to think of math not as a precarious Jenga tower, but as a bridge.
A bridge. Okay, I like that.
The foundational concepts are the load-bearing pillars. If you try to build the high-speed algebra highway on top of crumbling fraction pillars, the bridge collapses. But you don't fix the pillars by just slapping procedural mortar on them. You have to strengthen the core concept.
This aligns perfectly with the National Research Council's framework for mathematical proficiency. In our stack of sources, they identify 5 interwoven strands of proficiency. There's conceptual understanding, procedural fluency, strategic competence, adaptive reasoning, and a productive disposition.
Yes.
But the eternal battle in math education is always between the first two, right? Conceptual understanding versus procedural fluency, the why versus the how.
It's the oldest war in the staff room. But cognitive science has definitively settled this debate. Conceptual understanding must anchor procedural fluency. Always.
Always.
If you force a student to memorize a procedural trick without any conceptual context, like telling them, just cross out the 7, make it a 6, and put a 1 next to the 2 to borrow that knowledge, is completely sterile.
It's just an arbitrary rule.
Exactly. It is fragile.
Yeah.
It is a string of arbitrary rules that will be forgotten by next Tuesday.
But if they understand the concept, it acts like a cognitive safety net. Like if they deeply understand that the number 72 is made of 7 10s and 2 1s, and they understand that borrowing is actually decomposing one of those 10s into 10 1s, so they now have 6 10s and 12 1s.
Right. They own the math.
Exactly. Even if they forget the exact vertical algorithm, they could use their conceptual safety net to reconstruct the logic on the fly.
Exactly. Conceptual knowledge consistently supports procedural knowledge more strongly than the reverse. So how do we handle those crumbling bridge pillars without falling into the trap of endless deficit-based remediation? The field is moving heavily toward what we call just-in-time scaffolding, or acceleration.
Walk us through what that actually looks like in a real planning session. How is acceleration different from remediation?
Okay, so remediation is deficit-based. It assumes we must go back and fix every pothole from 2nd grade before we can do 8th grade math.
It's impossible.
Right. Acceleration is asset-based and highly targeted. Let's say you are teaching adding rational expressions next week. You know your struggling students are going to freeze because they struggle with finding common denominators with simple fractions.
Okay.
Instead of putting them in a remedial class that covers all of 4th grade math, you pull those specific students for a 15-minute targeted intervention on Wednesday. You use manipulatives, you build the conceptual understanding of common denominators, and you front-load that exact specific prerequisite skill.
Oh, I see. So when Monday rolls around and you introduce the rigorous grade-level algebra topic to the whole class, those struggling students already have the cognitive architecture warmed up and ready to go.
Precisely.
They get to participate in the rigorous thinking with their peers rather than being handed a watered-down worksheet in the back of the room.
It preserves their dignity and keeps them in the grade-level ecosystem. But we have to acknowledge a reality here. If we are consistently putting struggling students into rigorous, grade-level conceptual work, they are going to make mistakes, a lot of them.
Which requires a fundamental redefinition of the role of error in the classroom. In a procedural classroom, an error is a failure. It means you didn't follow the instructions. But in a thinking-based classroom, we have to adopt a generative diagnostic framework.
Right.
An error isn't a dead end. It is a milestone in schema development.
When a student makes a conceptual error, they are showing you the exact blueprint of their current understanding. The teacher's role is no longer to swoop in with a red pen and provide the correct answer.
So what do they do instead?
The teacher uses the error to diagnose the specific misconception and ask a targeted question that forces the student to confront the contradiction in their own logic.
And there's a biological reality to this process of working through errors that I found absolutely incredible in our sources. We talked earlier about how the brain shuts down due to anxiety.
Yeah.
But when a student engages in what we call productive struggle, when they are wrestling with a complex problem, making a mistake, realizing it, and adjusting their strategy, their brain is physically changing.
It is.
That specific type of struggle actually stimulates the production of myelin.
Myelin is one of the most fascinating mechanisms in neurobiology. It is a fatty protective covering that wraps around the axons of our nerve cells. You can think of it like the rubber insulation around a copper electrical wire.
Okay.
When you struggle to learn a new skill, the neural pathways in your brain fire. As you repeatedly fire those pathways through effort and correction, the brain wraps more and more myelin around that specific neural circuit.
And that insulation prevents the electrical signal from leaking out. It makes the neural pathway faster, more efficient, and more permanent. This struggle literally builds the brain's hardware.
It upgrades the circuitry.
But here's the practical question. How do we get a highly disengaged, deeply anxious 13-year-old to care about their myelin production?
You do something revolutionary. You explicitly teach them the brain science. High-performing teachers do not keep this neuroscience a secret in the faculty lounge. They bring it into the classroom.
They show the kids the brain scans.
Exactly. When you communicate to a student that the hot, frustrating sensation they feel when they are stuck on a math problem isn't a sign of stupidity, but is actually the physical, biological sensation of their brain synthesizing myelin to upgrade its hardware, I mean, it completely reframes the entire experience of school.
It breaks the fixed mindset. It normalizes the struggle. The frustration becomes the goal, not the obstacle.
It gives them a biological rationale for perseverance. So we know we need to shift to conceptual thinking. We need to utilize just-in-time scaffolding to build the bridge pillars, and we need to normalize errors to build myelin.
Right.
But abstract philosophy only goes so far. If I'm listening to this, I'm wondering, how do you actually physically orchestrate that in a room with 30 hormonal middle schoolers?
Which is the perfect bridge into our discussion on high-impact environmental models. If we want students to think differently, we have to redesign the physical and structural environment they're inhabiting. And we cannot have this conversation without diving deep into Peter Liljedahl's framework, Building Thinking Classrooms, or BTC.
Liljedahl's work is arguably the most disruptive force in math education right now, in the best possible way. He didn't just theorize, he spent 15 years in thousands of classrooms conducting micro-experiments.
Wow, 15 years.
Yeah. He was obsessed with figuring out what specific environmental factors triggered those passive studenting behaviors we discussed earlier. And his conclusion was radical. The physical environment itself, students sitting at individual desks in rows with the teacher standing in the front, is a massive trigger for passive mimicry.
The architecture of the room dictates the pedagogy. So how does BTC break that architecture? Let's look at the concrete tools.
The foundational tool of a thinking classroom is the use of vertical non-permanent surfaces, or VNPS, whiteboards, glass windows, chalkboards, anything vertical and erasable on the perimeter of the room.
Okay, let's dissect the psychology of this. Why vertical and why non-permanent? Let's start with vertical. What happens when you make a kid stand up to do math?
Biologically, standing up increases blood flow to the prefrontal cortex, which immediately aids executive functioning. Behaviorally, verticality completely disrupts the physical posture of disengagement.
Oh, because they can't slouch.
Right. When a student is sitting at a desk, they can slump, they can hide their paper with their arm, they can zone out. When they are standing at a whiteboard with two peers, their entire body is exposed to the room. They are physically oriented toward the task and toward each other. It makes hiding socially awkward and physically difficult.
That makes perfect sense. But the non-permanent aspect of the use of a dry erase marker instead of a pencil and paper seems to be where the real psychological magic happens.
It goes right back to lowering the cognitive and emotional cost of failure. Liljedahl found a staggering statistic in his research. When you give a student a complex math task on a permanent piece of paper, they might stall for up to 3 full minutes before writing a single digit.
3 minutes.
Yes.
Because writing on paper feels definitive. It feels permanent.
Yeah.
If they write the wrong first step, they have to use an eraser, it leaves a smudge, it leaves a physical record of their failure. The anxiety spikes.
Exactly. But when you put those same students standing at a whiteboard with a dry erase marker, they start writing within 20 seconds.
20 seconds versus 3 minutes. That's incredible.
Why? Because they know that if they go down the wrong path, a single swipe of a cloth completely erases the evidence. It radically lowers the emotional stakes, which dramatically increases intellectual risk-taking.
And they aren't standing at these boards alone. They are in groups.
Yeah.
Visibly random grouping, or VRG. Now, I have to stop here and push back on behalf of every educator listening.
Okay, go for it.
Every single teacher has tried group work. And we all know the classic pitfalls. Doesn't grouping kids just mean the smart kid does all the heavy lifting while the struggling kids hide in the corner and talk about video games?
That is exactly what happens in strategic grouping.
Oh, okay.
When teachers spend hours engineering groups, putting one high achiever, two middle achievers, and one low achiever together, the students instantly figure out the social hierarchy. The roles are implicitly assigned the second they sit down.
The high achiever assumes the role of the mini teacher, and the struggling student assumes the role of the passive scribe.
Yes. They play the part they were assigned. But Liljedahl discovered that when the grouping is visibly random, meaning the teacher literally shuffles a deck of cards or draws popsicle sticks in front of the students every single day to form groups of 3, it completely breaks down those social cliques and academic hierarchies.
Because it's a completely level playing field every 24 hours.
Yeah.
The social dynamic doesn't have time to calcify.
Exactly. And when you combine random groups with the vertical whiteboards, you create an environment of extreme knowledge mobility.
Knowledge mobility.
If your group of 3 is completely stuck on a problem, you don't raise your hand and wait 5 minutes for the teacher to rescue you. You just turn your head, look across the room at another group's whiteboard, and borrow an idea.
Oh, that's brilliant.
The knowledge flows horizontally between peers rather than just flowing top-down from the teacher.
That is a brilliant democratization of the classroom. It shifts the authority of the knowledge from the teacher's answer key to the collective intelligence of the room. Now, alongside BTC, our sources emphasize UDL, Universal Design for Learning, and something called the CRA sequence.
Yes, very important frameworks.
I want to clarify UDL because I think a lot of educators use UDL and differentiated instruction interchangeably. I was reading through the stack, and the sources treat them like completely different philosophies.
They are entirely distinct approaches to learner variability. Differentiated instruction is fundamentally reactive. In a DI model, the teacher designs a standard one-size-fits-all lesson. Then, during the lesson, the teacher observes that a specific student is struggling and reacts by retrofitting the content.
Like giving them a modified worksheet or pulling them into a small group.
Right.
It's like building a standard staircase, realizing someone has a wheelchair, and then scrambling to bolt a wooden ramp over the stairs after the fact.
That is the perfect architectural analogy. UDL, on the other hand, is proactive. Universal Design for Learning assumes from the very first moment of lesson planning that learner variability is the norm, not the exception.
Yeah.
It builds accessibility into the core architecture of the lesson. You build the building with a universal ramp seamlessly integrated into the entryway from day one so everyone can access it without asking for special permission.
And in the mathematics classroom, one of the most powerful universal ramps we have is the CRA sequence. Concrete, representational, and abstract.
The CRA sequence is non-negotiable for struggling learners. It is a pedagogical progression that respects the cognitive load of abstract logic.
I love how the sources frame this. It's exactly like learning a foreign language. If you want to teach a toddler the concept of an apple, you don't start by writing the letters A, P, P, L, E on a chalkboard. That's abstract nonsense to them.
Right.
The concrete phase is handing them a physical apple. They feel the weight, they bite it, they taste it. The representational phase is showing them a 2D drawing or a photograph of an apple. And only then, after the schema is built, do you move to the abstract phase, the written word.
Exactly.
If you jump straight to the abstract symbols with a struggling math student, it's literally a foreign language they cannot decode.
Let's apply that language acquisition analogy to middle school algebra. Let's say we are teaching students how to solve a multi-step equation, like 2x plus 3 equals 11.
Okay.
The traditional method jumps straight to the abstract, writing the symbols on the board and telling students to subtract 3 from both sides. For a struggling learner, those symbols hold no semantic meaning.
So how do we start concrete?
In the concrete phase, we give the student physical manipulatives like algebra tiles. They physically place 2 green rectangular X tiles and 3 yellow square unit tiles on the left side of a balance mat, and 11 yellow unit tiles on the right.
And then to solve it,
They physically pick up and remove 3 yellow tiles from both the left and the right sides. They are touching the math. They feel the principle of equality in their hands.
and then we transition to representational.
Right. We take the physical tiles away. Now they draw a tape diagram or an area model on their whiteboard that represents the tiles. They draw a long box for X and small squares for the units. They cross out the squares in their drawing. This bridges the physical, tactile world to the mental, visual world.
And only after they have mastered the drawing do we introduce the abstract equation with numbers and variables.
Yes.
Yeah.
Because by the time they get to the symbolic manipulation, the abstract symbols are finally tethered to a conceptual reality. When they write -3 on the paper, their brain isn't just following an arbitrary rule. Their brain is visualizing the removal of those 3 yellow tiles. The abstraction has meaning.
And this philosophy of building meaning from reality ties perfectly into another framework from our sources, problem-based learning, or PBL, and specifically realistic mathematics education, RME.
Realistic mathematics education was developed at the Fordenthal Institute in the Netherlands, and it completely flips the traditional script of math instruction.
How so?
The core tenet of RME is that mathematics should not be taught as a finished product, a set of pre-packaged formulas handed down from the teacher. Instead, math should be experienced as a human activity.
They use a term I highlighted, guided reinvention.
Guided reinvention is profound. Instead of giving students the formula for dividing fractions, you give them a realistic, imaginable context. Let's say sharing a limited amount of sub-sandwiches equally among a large group of people. You let the students struggle with the reality of the problem first.
And through that struggle, they engage in what RME calls mathematization. First, horizontal mathematization, where they translate the real-world sandwich problem into informal mathematical models. They draw the subs, they slice them up visually, they figure out the fair shares.
And then, the teacher guides them into vertical mathematization, refining those informal drawings into formal symbolic rules. They invent the algorithm themselves. They reinvent the mathematics under the guidance of the teacher.
And this isn't just idealistic theory. The data on PBL is striking. The sources reference a comprehensive 2022 dissertation study of middle schools in a massive New York City district.
Oh, that study is incredible.
They compared classrooms using traditional direct instruction to classrooms implementing problem-based learning. The schools using PBL didn't just show significantly greater growth in standardized math scores, they also reported vastly more positive perceptions of the school community from both teachers and students.
It works academically, and it heals the social-emotional climate of the room.
It does. But we have to be honest with our listeners. Implementing a thinking classroom or a problem-based learning model is messy. It requires the teacher to completely embrace the chaos of the struggle.
Oh, it is organized chaos. Which brings us to the operational reality of the classroom. You've set up the vertical whiteboards, you've randomly grouped the kids, you've given them a great real-world sandwich problem, and now they're completely stuck.
They're frustrated.
Exactly. How do you, as the responsive architect, make sure this struggle remains productive and doesn't just trigger that executive function shutdown and the math anxiety we diagnosed at the very beginning?
This is the art of teaching. We are trying to keep students in what cognitive psychologists call the zone of proximal discomfort. It's a variation of Vygotsky's zone of proximal development.
Right.
It is that fragile, highly active sweet spot between complete boredom where the task is too easy and complete frustration where the task is so hard it triggers the threat response.
It's the Goldilocks zone of cognitive load. But how do we distinguish between productive and destructive struggle?
A good question.
Productive struggle occurs when the goal is clear and the student views their effort and their errors as necessary tools for sense-making. They know they are stuck, but they have pathways to try.
And destructive struggle.
Destructive struggle is when the goals feel hazy, the task feels arbitrary, and the effort just reinforces their pre-existing feelings of inadequacy.
So how does a teacher actively manage that in real time, in a chaotic room with 30 kids arguing at whiteboards?
It requires highly structured, almost invisible orchestration by the teacher. And the gold standard framework for this is Margaret Smith and Mary Kay Stein's 5 practices for orchestrating productive mathematics discussions. It takes the chaos of group work and structures it into a cohesive mathematical narrative.
Let's walk through these 5 practices in exhaustive detail because this is the playbook for the responsive architect.
Okay, let's use a specific scenario. Let's say the teacher has given the class a system of equations problem hidden in a real-world context, choosing between 2 cell phone plans.
Okay, classic problem.
Right. Plan A has a $50 flat fee plus $10 a gigabyte. Plan B has no flat fee but costs $20 a gigabyte. The goal is to find out when the plans cost the same. What is practice 1?
Practice 1 is anticipating. This happens the night before, sitting at your desk. The teacher does not just solve the problem using the most efficient algebraic method.
No.
The teacher explicitly predicts every single way the students will approach the task, including the informal strategies, the correct models, and crucially, the specific misconceptions they will fall into.
So the teacher anticipates that Group 1 might try to draw a messy graph. Group 2 might try to make an input-output table, and Group 3 is going to make the classic misconception. They will forget about the $50 flat fee for Plan A and just assume it starts at 0.
You have to know where the traps are before the kids even enter the room.
Exactly, which leads directly to practice 2, monitoring. The lesson has started. The students are at their vertical whiteboards arguing about cell phone plans. The teacher is not standing at the front. The teacher is circulating with a clipboard, actively observing and recording the specific strategies each group is using.
They aren't just walking around doing classroom management, making sure kids aren't poking each other with markers. They are data mining. They are mapping the cognitive landscape of the room in real time.
Yes, they are looking at their anticipation sheet and checking off who is doing what. This active monitoring leads to practice 3, selecting. This is where the orchestration becomes masterful.
Okay, how so?
As the group work winds down, the teacher intentionally chooses specific boards or pieces of student work to highlight for the whole class discussion.
And this is a massive departure from traditional teaching. In a traditional room, the teacher just says, who got the right answer? Great, Sarah. Come show us how you did it. You call in the fastest kid who used the standard algorithm.
Which completely alienates the struggling learners. In the 5 practices, you select strategically based on the narrative you want to build. You might actually select the group that made the zero-intercept misconception first, because you know it will spark a debate.
Oh, I see.
Then you might select the group that made the messy table. And finally, the group that wrote the formal equations.
And determining that order is practice 4, sequencing.
Precisely. Sequencing is deciding the exact chronological order in which the selected solutions will be shared. You are building a cognitive staircase for the class.
A staircase, yeah.
You start with the most accessible, visual, informal strategy like the table. Everyone can understand the table. Then you sequence to the graph, which is slightly more abstract. Then you sequence to the formal algebraic equation.
It's building a narrative arc where every student, regardless of their foundational gaps, can find an entry point into the discussion. Which brings us to the final practice, connecting.
Connecting is the culmination of the lesson. The teacher doesn't just let the groups present their work like a show and tell. The teacher asks targeted, probing questions to help the students see the mathematical links between the different representations.
Like, where do we see the $50 flat fee from Group 2's table represented in Group 4's graph? Ah, it's the Witcher intercept. And where is it in Group 5's equation? It's the constant B.
Yes, you are knitting the conceptual threads together.
And this is exactly what Peter Liljedahl calls consolidation. I love this specific point in our sources. Consolidation in a thinking classroom must be bottom-up.
Bottom-up consolidation means the teacher is leveling the room by synthesizing the students' own informal work into the formal mathematical notation. You don't bring them back to their desks and say, okay, here's the real way to do it.
Right.
You take their messy, brilliant logic from the whiteboards and you layer the formal academic vocabulary on top of it. The authority of the knowledge comes from the students, not the textbook.
Okay, we've mapped out this beautiful theory-backed environment. We've got the whiteboards, the random groups, the 5 practices. But let's be incredibly real for a second.
Okay.
It is 8 a.m. on a Monday morning. A student with severe math anxiety, executive dysfunction, and a deeply fixed mindset walks into your room. They sit down. How do you actually get them to pick up the marker without triggering that freeze response? So let's move into our concrete, tactical classroom moves.
This is where the rubber meets the road. Let's talk about task initiation. To overcome that executive function freeze, we need to deploy antecedent strategies.
Antecedent meaning before the behavior.
Interventions we execute before the cognitive threat can even register in the student's brain. We have to lower the activation energy required to begin.
One of the simplest, most brilliant antecedent strategies from the sources is the use of start here entry points. It's literally taking a physical sticky note and placing it on a student's desk next to a single problem on a worksheet with the words, start with this one. Why is something so simple so effective neurologically?
Because it aggressively reduces visual and cognitive overwhelm. When a student with ADHD or high anxiety sees a paper with 20 complex word problems, their brain perceives a massive, unmanageable threat. The working memory shuts down.
Right.
By using a sticky note to narrow their entire visual field to a single, small, isolated action, you completely lower the barrier to entry. You bypass the threat response.
Make it achievable. The same logic applies to another move. The visual micro checklist. Instead of handing a student a complex 10-step grading rubric, you put a Post-it on their desk with a maximum of 3 microscopic steps.
Give me an example.
Step 1, gather a pencil and calculator. Step 2, read the prompt out loud to your partner. Step 3, highlight the numbers.
It externalizes the executive functioning. The brain doesn't have to spend RAM planning the sequence of actions. The sequence is offloaded onto the paper. Another powerful initiation routine is the silent start time.
Yes, the protocol where the first 3 to 5 minutes of a complex task are completely, strictly silent. No talking to group members, no asking the teacher questions. You just sit in silence, gather your materials, read the prompt, and formulate your initial thoughts.
It is so effective.
Why does forcing silence help the struggling learner?
Because in a collaborative environment, the fastest processors, the kids who calculate quickly, will immediately dominate the airspace. Before a struggling student has even finished decoding the first sentence of the word problem, the fast processor is already shouting out strategy ideas.
Which is so deflating.
It immediately triggers feelings of inadequacy and causes the struggling student to mentally check out. The silent start time forces a quiet activation window. It gives the slower processors the dignity of time to orient themselves to the problem space without social pressure.
I love that. Now, once you've successfully initiated the task, you need a problem structure that sustains their engagement without hitting a brick wall. We call these low-floor, high-ceiling tasks.
Yes.
Tasks that are so accessible anyone can start them, but so mathematically rich they can stretch to infinity in complexity. And the absolute masterclass of this is Dan Meyer's 3-act math tasks. Let's unpack the architecture of the 3 acts.
3-act math is a brilliant narrative structure that relies on curiosity rather than compliance. Act 1 is the hook. The teacher plays a short, highly engaging video or shows an image of a real-world scenario. But crucially, and this is the genius of it, there are no numbers and there is no math question provided.
My favorite example is the video of a guy pouring ping pong balls into a large glass cylinder. You just watch the video. That's it. It's designed purely to spark natural human curiosity. The teacher just asks, what do you notice and what do you wonder?
And because there are no numbers and no formal math symbols, it is completely non-threatening. Even a student with the most severe math trauma can safely raise their hand and guess, I wonder how many balls will fit in the glass.
They have generated the math problem themselves. They have bought into the narrative.
Right, and then they make an initial guess. I think it's 50. I think it's 500. They've established a stake in the outcome. Then we transition to Act 2, the information.
Okay, what happens in Act 2?
At this point, the students realize their guess isn't enough. They need actual data to solve the problem they just created. So instead of the teacher handing them a worksheet with the dimensions, the students have to ask the teacher for the specific information they need.
We need the volume of the cylinder. We need the diameter of one ping pong ball.
Exactly. The teacher acts as the gatekeeper of the clues, providing the data only when requested. This is where the heavy lifting of the mathematics, the formulas, the calculations actually happens.
But cognitively, it feels entirely different because the students are pulling the math from the teacher to solve a mystery, rather than the teacher pushing arbitrary math onto them.
It's an investigation. And then the payoff. Act 3, the reveal. The teacher plays the end of the video showing the actual ping pong balls filling the glass, and the students compare their calculated mathematical models with the messy reality of the physical world. It is an incredible narrative arc that completely bypasses math anxiety.
Alongside 3-act tasks, the sources highly recommend open middle problems. A traditional math problem is closed at the beginning and the end. There's one starting equation, one path to solve it, and one right answer.
Right.
An open middle problem usually has a defined start and end, but the space in between is completely open to trial and error.
Like giving students an equation with empty boxes and telling them they can only use the digits 0 through 9 exactly once to make the equation true.
Yes, it forces them to experiment, to plug things in, to fail, and to adjust. It completely dismantles the toxic idea that there is only one correct, teacher-sanctioned path to a solution.
It builds incredible mathematical stamina. But to support that stamina, especially for students with processing difficulties or multilingual learners, we have to integrate language and sense-making routines. We cannot assume that reading a math problem is the same as reading a novel.
Which brings up my absolute favorite tactical routine from the entire stack of sources, the 3 Reads Protocol. This is the ultimate silver bullet cure for the disease educators call number plucking.
Number plucking, it's so common.
You know number plucking. It's when a kid looks at a word problem, completely ignores the text, grabs the 2 numbers they see, and just randomly adds or multiplies them together because they want the cognitive load to end.
Number plucking is a desperate symptom of cognitive overload. The student cannot process the complex language and the mathematical operations simultaneously, so they jettison the language.
And the 3 Reads Protocol cures this.
Yes, by systematically slowing the brain down and isolating the cognitive demands. You read the exact same word problem 3 separate times, each with a very specific isolated lens.
Let's walk through a concrete example. Let's say the problem is Marcus goes to the store with $20. He buys watermelons that cost $3 per pound. If the watermelons weigh 2 pounds each, how much change will he get?
Okay, good problem.
In the first read, the teacher reads it aloud, and they might actually use a black marker to cross out the numbers. The only question asked is, what is this story about?
The goal here is purely visualization and reading comprehension. The students discuss the context without any mathematical pressure. It's a story about a guy named Marcus buying fruit at a store. They are building the mental stage.
Once the stage is set, we do the second read. We uncover the numbers. Now the question is, what are the quantities and units in this situation?
Now, the students are identifying the data structures. They identify the explicit data. He has $20 total. The cost is $3 per pound. And the implicit data, he is buying a certain number of watermelons. They are mapping the parameters of the problem.
And finally, the third read.
The third read asks the pivotal question. What mathematical questions could we ask about this situation? Notice we haven't even looked at the actual question printed on the worksheet yet.
Oh, wow.
The students generate possibilities. We could ask how many watermelons he can afford. We could ask how much one whole watermelon costs.
This protocol ensures that the student has fully conceptualized the entire architecture of the problem before they ever pick up a calculator to perform an operation. It is forced, structural sense-making.
It's brilliant. Alongside text-based routines, we also need visual routines like which one doesn't belong, or WODB, and notice and wonder. In WODB, you show 4 images, shapes, or equations on the board. The secret is that there is no single right answer. A valid mathematical argument can be made for any of the 4 being the outlier.
You ask the students to justify their choice. These routines are so powerful because they completely decenter the teacher as the sole arbiter of truth. The students are debating each other, finding their own knowledge gaps, and building logical arguments.
But managing these student-led routines requires a massive shift in how the teacher physically speaks and interacts. This is the realm of talk moves. If you are going to transition from evaluator to choreographer, you have to master the micro techniques of classroom discourse.
The most famous, and arguably the most difficult talk move, is wait time. It is the practice of asking a question and then literally waiting 3 to 5 agonizing seconds in total silence before calling on anyone or speaking again.
It sounds incredibly simple, but if you record a typical classroom, the average teacher wait time is less than 1 second.
Less than 1 second.
Yes. It is physically uncomfortable for adults to endure silence. But that 3 to 5 second cognitive window is vital. It allows the slower processors to translate the language, search their memory bank, and formulate an idea. If you jump in after 1 second, you are permanently cutting off the thinking of half your room.
Another crucial talk move is revoicing. A student might give a really messy, halting, informal explanation of their strategy. The teacher listens and then says, "So what I hear you saying is that the relationship is proportional because..."
Yeah.
And the teacher paraphrases the student's logic using formal academic vocabulary.
Revoicing accomplishes 2 things simultaneously. It deeply validates the student's original intellectual contribution, showing them their thoughts matter, while simultaneously elevating their informal language into the formal mathematical register.
And then there's the 80-20 rule. Our sources suggest that expert teachers target 80% of their questions toward conceptual understanding, even if the procedural answer the student gave is completely correct.
Right. So a kid says the answer's 14, and instead of the teacher saying, "Good job, next question," the teacher says, "You're right, but how did you know to divide instead of multiply?"
It proves to the room that the why matters far more than the what. It disrupts the idea that the goal of math is just to produce a number.
One more routine from the sources that we absolutely have to highlight is my favorite no. I think this is a masterpiece of classroom culture building.
Yes, my favorite no.
It is the ultimate routine for normalizing and weaponizing error for good. The teacher collects student work on a small problem like an exit ticket. They quickly sift through the pile and intentionally select an incorrect answer that features a brilliant, highly common conceptual misconception.
Okay.
They rewrite that exact incorrect work anonymously on the whiteboard and announce to the room, "This is my favorite no."
You are literally celebrating the mistake.
Yes. But the structure of the analysis is key. The teacher first asks the class, what did the student do perfectly? They analyze and praise the solid logic, the correct setup, the neat organization. They validate the thinking. Only then do they ask, okay, where did the reasoning break down? What trap did they fall into?
It teaches mental model repair. And because it's anonymous, it makes the error a communal puzzle to be solved by the team, rather than a personal, shameful failure of an individual.
It's beautiful. But this brings us to a critical inflection point. Because even with all these amazing routines, the whiteboards, the 3-act tasks, the wait time well-intentioned teachers can accidentally sabotage their own efforts.
Oh, no.
They can inadvertently reinforce the exact disengagement they are trying to cure. We have to look at the common mistakes educators make.
Let's get into it. What is the biggest trap?
The most pervasive, damaging mistake is what cognitive scientists call the trap of the rescue, or scaffolding down. And it stems entirely from teacher empathy.
Okay, paint a picture of this for me. What does the rescue look like in real time?
A student is working on a highly complex proportional reasoning problem at their whiteboard. They hit a wall, they get frustrated, they drop their marker, they look at you with those defeated eyes, and they say, I don't get it. I can't do this.
That's heartbreaking.
The teacher's immediate instinct out of deep empathy and a desire to alleviate the student's discomfort is to step in and water down the problem. They break the complex task into tiny, bite-sized procedural pieces. They essentially do the thinking for the student. They say, okay, don't worry about the whole problem. Just take this number, multiply it by this number, and tell me what you get.
We do it because we hate seeing kids struggle. We want them to feel successful.
Exactly. But when you do that, you have stolen the cognitive event. You have stolen the productive struggle. You have rescued them from the exact process that builds myelin.
Wow.
The cardinal rule of a thinking classroom is you must scaffold up, you never scaffold down. You maintain the rigor of the problem, but you provide tools to reach it.
So let's make that concrete. If a student is stuck on a rich proportional reasoning task because their working memory is completely bottlenecked trying to multiply 2 decimals, what do I do instead of making the problem easier?
You provide a conceptual tool to bypass the bottleneck. You give them what I call a calculator permission slip. You say, I can see you are getting bogged down in the decimal multiplication. You can use a calculator for the arithmetic, but I want you to focus purely on setting up the structural ratio correctly on the board.
You remove the extraneous cognitive load so they can focus entirely on the high-level logic.
Exactly. You keep the cognitive demand high. Another way to avoid the rescue is through the questions you ask. Instead of giving a hint, you use an assessing question or an advancing question.
Like what?
You approach the board and ask, tell me what you've tried so far, or how could you represent this information visually? You refuse to pick up the marker. You put the cognitive ball firmly back in their court.
It communicates a deep belief in their capability. And that ties directly into another massive area of unintentional harm, the feedback teachers provide. We have to clearly distinguish between comfort-oriented feedback and strategy-oriented feedback.
Comfort-oriented feedback is the classic toxic empathy. It's when a student fails a summative assessment and the teacher pulls them aside, pats them on the shoulder, and softly says, hey, it's okay. Math is just really hard for a lot of people. You are such a great artist. You have other talents.
It sounds incredibly kind in the moment.
But extensive psychological research shows that comfort-oriented feedback secretly signals to the student that the teacher has low expectations of them. It confirms the student's fixed mindset. It essentially translates to, I agree with you, you are fundamentally incapable of doing this math.
That is devastating.
It is. Instead, we must rigorously employ strategy-oriented feedback. When the student fails, you look at the work and say, let's look at the strategy you used here. This specific approach didn't work for this problem. What is another mathematical model we could apply here?
This communicates high expectations. It reinforces the reality that mathematical success is a matter of deploying the correct strategy and exerting effort, not possessing an innate genetic gift. And the timing of this feedback is critical, right? The neuroscience and the sources regarding feedback timing is absolutely wild. I think it completely upends how we grade.
It really does. We have to understand the neurological difference between immediate feedback and delayed feedback. Immediate feedback, like when a student is using an adaptive computer program that flashes a green check mark or a red X, the second they hit enter, activates the basal ganglia.
The basal ganglia is the reward and habit center of the brain.
Right. That immediate dopamine hit is fantastic for motivation, and it's highly effective when you are trying to build rapid procedural fluency, like memorizing multiplication facts.
It keeps you in a flow state for quick, repetitive calculations.
But if our goal is to build deep, complex, conceptual understanding, the load-bearing pillars of the bridge, we actually need delayed feedback. Delaying the feedback forces the brain to activate the hippocampus.
A hippocampus.
The hippocampus is essential for long-term memory integration, reflection, and schema building. If you give a student the answer immediately upon them getting stuck on a complex problem, you completely short-circuit the hippocampal processing. You prevent the memory from taking root. Sometimes, the most powerful pedagogical move a teacher can make is to let a student sit with the ambiguity overnight.
That is mind-blowing. Let them sleep on the unresolved problem so the hippocampus can process it during REM sleep. That is biology working for you. Finally, the last common mistake we need to address is ignoring the affective dimension, ignoring what we call math trauma.
We cannot treat these middle schoolers as purely cognitive, calculating machines. Many of these struggling learners associate mathematics with intense physical and emotional anxiety. And very often, that trauma stems directly from well-intentioned elementary school practices, specifically public high-stakes time tests.
The dreaded mad minute. I still get a pit in my stomach thinking about a teacher standing over me with a stopwatch while I try to do 50 division problems.
Exactly. It creates an indelible link in the brain between mathematics, speed, and panic. To cure this trauma in middle school, we must definitively and aggressively decouple speed from mathematical ability. We have to tell students, being fast at arithmetic does not make you a good mathematician, it makes you a good calculator. Mathematics is about deep, slow, structural reasoning.
But practically speaking, we still need them to have fact fluency, right? We talk about how lack of fluency eats up the RAM. So how do we build that fluency without triggering the stopwatch trauma?
We use private, self-managed, low-stakes routines. The sources highlight an intervention called the Cover Copy Compare routine. A student is given a list of correct math facts. They study the fact, they physically cover it with their hand, they write it from memory on a whiteboard, and then they uncover the original to check their accuracy.
That's it.
That's it. It takes 10 minutes a day. It effectively builds the myelin pathways, but crucially, it is completely private. There is no public shaming. There is no ticking clock displayed on a smartboard. There is no comparing scores with a neighbor. It builds the necessary cognitive muscle memory in an environment of total psychological safety.
Okay, we have covered an unbelievable amount of ground today. Let's take a breath and synthesize this massive journey for the educator who has been listening and taking notes. We started by diagnosing the real root of the issue, understanding that your struggling students aren't inherently lazy or defiant.
No, they're not.
They're actively battling cognitive load bottlenecks, their working memories being hijacked by intrusive anxiety, their executive functions are freezing, and they are carrying the heavy cultural armor of a fragile math identity and stereotype threat.
And understanding that biology demands a paradigm shift. We must move away from the endless deficit-based remediation of isolated procedures. We must pivot toward front-loading conceptual understanding, building the pillars of the bridge, and creating a classroom culture where errors aren't punished, but are explicitly celebrated as the exact biological moments the brain produces myelin.
We looked at how to fundamentally redesign the physical and social architecture of the room, using building thinking classrooms, disrupting passive studenting behaviors by putting kids in visibly random groups at vertical non-permanent surfaces.
Right.
We walk through the UDL framework and the essential concrete representational abstract sequence to ensure that abstract algebra symbols actually mean something tangible to the learner.
We discussed the art of orchestrating the chaos of productive struggle using the 5 practices, anticipating misconceptions, monitoring the room, selecting the right work, sequencing it logically, and connecting it all together, ensuring that the final consolidation of knowledge is a bottom-up synthesis of the student's own brilliant logic.
We armed you with tactical Monday morning moves, using sticky notes and micro checklists to bypass the executive function freeze, deploying the curiosity-driven 3-act math tasks, and using the 3 reads protocol to kill number plucking once and for all.
And finally, we warned against the toxic empathy of the rescue, urging you to scaffold up, use strategy-oriented feedback to engage the hippocampus, and definitively decouple speed from mathematical intelligence.
It is a profound shift in practice. But as we synthesize all of this, it raises a massive existential question as we look toward the future of education.
It really does.
Hit me. What's the next frontier?
The sources introduce a concept called the algorithmic shift and the impending danger of knowledge encapsulation in the era of artificial intelligence.
Oh, this is fascinating, because if we just spent the last hour meticulously detailing how productive struggle is the exact biological mechanism that builds the brain's hardware, what happens to a generation of students who can pull out a smartphone, snap a picture of a complex system of equations, and have an AI instantly spit out the fully formatted, step-by-step solution, completely bypassing the struggle?
That is the existential threat to cognitive development. If students perpetually outsource the productive struggle to a machine, they suffer from knowledge encapsulation. They get the correct output, but the underlying logic, the structural reasoning, remains completely hidden inside the black box of the AI's algorithm.
So they don't do the work.
Their neural pathways don't fire, the myelin is never produced, their brains literally do not grow.
So, as educators master the art of teaching with struggle, the next great pedagogical challenge will be designing environments and assessments that actively audit a student's human logic. We have to foster what the sources call digital immunity.
Exactly. In a world where the procedural calculation can be completely and flawlessly outsourced to a silicon chip in half a second, the value of the human mathematician is no longer in computing the answer.
Right.
The value is in the setup, the structural reasoning, the ability to formulate the right question, and the ability to justify the logic. We must shift our assessments to evaluate their ability to verbally defend their mathematical models, to critique intentionally flawed AI outputs, and to apply abstract concepts to the messy reality of the physical world.
The X-ray machine of diagnosis is changing yet again.
It is continuously evolving.
At the very beginning of this deep dive, we talked about how a medical X-ray is clean, simple, and binary. A broken arm is just a broken arm. But a struggling middle school math student is a wildly complex, beautiful ecosystem of cognitive load, fragile identity, executive function, and biological potential.
Very true.
You cannot just point at a failed benchmark test, point to the D- and say, there's the break. As a responsive architect, you have to build an environment where the student feels psychologically safe enough to show you their muddy, imperfect thinking. A room where you can trace their evolving logic on a vertical whiteboard, where you can guide them through the messy, frustrating, incredibly rewarding struggle of real mathematics.
Perfectly said.
Thank you so much for joining us on this deep dive. Our challenge to you, the educator: do not try to change everything at once. Pick just one single routine we talked about today. Put up a non-permanent surface on your wall, try implementing a 3-act task to spark curiosity, or institute a 3-minute silent start time tomorrow morning. Redesign the architecture. Transform the struggle. We'll see you next time.